Some of this stuff is going to be review from Algebra 2, but I want to make sure that we're all familiar with the terminology, and then we'll start looking at some calculus applications when we talk about limits, okay? So first of all, a sequence is a function, even though in Algebra 2 we probably didn't call it a function, but it's a function whose domain is a subset of the integers, okay, meaning counting numbers, all right? We can write an explicit form, so this one is an explicit, oops, that's not how you spell explicit. There we go. An explicit form of the function as f of n, and then that means that n, if we're talking about our nth term, so whatever n is, that a sub, that number would be whatever we get if we plug n into the function. So this is explicit as opposed to recursive. If you remember, recursive formulas or recursive sequences are sequences that are defined where the nth term is maybe something from the previous term. So like a sub n plus 1 equals 3 minus a sub n, something like that. We're not going to deal with those, just explicitly defined sequences here. Okay, these braces here mean that it's a set, so it's the set of the terms a sub n. Okay, so a is not a variable and n is not an operation. N is the numbering system and a just means that it is a sequence. Okay, so it's like the name of the sequence, a sub n, b sub n, etc. All right, so for this first example, we've got a sub n equals cosine of pi n, and we want to write the first four terms, meaning I'm looking for, oh, also the starting point, unless it says otherwise, your starting point is going to be 1, okay? We could start at a sub 0 sometimes. You'll see some of that. You could start at a sub 2. Maybe a sub 1 doesn't exist because maybe we've got like divided by n minus 1 and then you can't divide by 0. But for the most part, unless it says otherwise, start with n equals 1. Okay, so a sub 1 is going to be equal to cosine of pi times 1, which we know to be negative 1, all right? A sub 2 is going to be cosine of pi times 2, so I'm just taking my n values and plugging them in for n, okay? And so then we get 1. A sub 3 is cosine of pi times 3, which again is negative 1, and then a sub 4, cosine of pi times 4, cosine of 4 pi is again positive 1. All right, so we kind of see that that sequence is just going to be a list of negative 1, positive 1, negative 1, positive 1, negative 1, positive 1, and we'll just keep alternating back and forth, okay? For the second one, for b sub n, so we'll call this part A, part B. For this one, we have 2 plus negative 1 raised to the nth. This is going to be a notation that you'll be pretty familiar with as well. And what this does is it means that we alternate back and forth between positive and negative 1 as n increases, all right? So for b sub 1, I have 2 plus negative 1 to the first, so that is just 1, okay? B sub 2 would be 2 plus negative 1 squared, so that's going to be a 3. B sub 3 would be 2 plus negative 1 to the third, all right? And so, again, we're back, excuse me, again, we're back at 1. B sub 4 back at 3. So this is another example of one that is just alternating back and forth between two values. Okay. So some more terminology here. If the function, the sequence a sub n, which is the function f of n, is defined by f of x, so the difference between this notation and this notation, pretty much they're the same thing, but really this is more something that we would think of as continuous. This is something that we would think of as discrete. Okay, discrete meaning it's just a list of values. Doesn't have to be a finite list of values, but think about like data points here as opposed to a continuous function over here, all right? And then, so if the function is defined by f of x and the limit of that function at infinity is equal to some value L, in other words, the limit does exist. That's what we're saying here. So it's not infinity, it's not, does not exist, it's not something alternating. Then the limit as n approaches infinity of the sequence is also L, okay? If that is not true, then the sequence diverges. So let me kind of restate what that part is telling us right here. And actually, I'm going to add some more room so I can write it, okay? So what this is saying is if we take whatever the notation for the sequence is, okay, so up here, cosine pi n, for example. If we take that notation and think about it as a function, so I would just say, you know, f of x equals cosine of pi x. And we look at this and the limit as x approaches infinity of this function exists, okay? Then we can say that the sequence has a limit as well. The limit of the sequence exists also, okay? In fact, is the same thing. Now, for this particular example, the limit as x approaches infinity of this does not exist, so we would say that this one diverges, okay? So this one, so we'll say the limit does not exist, so a sub n diverges. All right, same thing with b. This one is just jumping back and forth. It doesn't, this as a function does not have a limit, so it also diverges. Okay, and then the important conclusion here is that the sequence behaves like the function. So even though the sequence is just not a finite, but a discrete set of points, okay, the sequence, so here's our important part. The sequence behaves, like the function. Okay, this 1.2 that I have up here in section 1.2 from the book where we talked about the precise definition of a limit, and we use delta epsilon proofs to do that. I think that we actually have not talked about that yet. We skipped it back in chapter 1, so this is just something to refer back to that, but we will either not talk about that yet or not talk about it at all. So you don't need to worry about that right now. Okay. All right. So you can look at page 450 for some limit properties. These should look pretty familiar because we've talked about limit properties. And then also remember the squeeze theorem. We saw this in section 1.3 in the book. And then we saw it again when we used the squeeze theorem to prove the first fundamental theorem. Remember how we said that if we know that one function is greater than or equal to another, which is greater than or equal to a third, and then at some point the top function and the bottom function have the same limit, then the middle function has to have the same limit as well. So just as it applies to functions, it also applies to sequences. Okay, one specific type of sequence that is going to show up a lot is a geometric sequence. So this is one that you saw a lot of in Algebra 2, okay? Arithmetic and geometric sequences and series were two of the very common ones that you looked at and had a bunch of formulas for, okay? Arithmetic we don't really care so much about, but here geometric is going to be a really big deal in this chapter, okay? So a geometric sequence is something that can be written in the form c times r to the n, okay? C is some constant, r is some constant as well, and r is called the ratio. Okay, r is called the ratio, and it is raised to the nth power. And then we also know from Algebra 2 that if r, or the absolute value of r, is less than 1, then that means the sequence will converge. Okay, so the sequence will converge. And again, that may be something that you remember from Algebra 2, okay? If the sequence converges, then that also implies that, based on what we talked about up here, that the limit at infinity does have to exist, okay? So the limit, actually, let me write it this way. The limit as n approaches infinity of a sub n will exist. Okay, will exist. Now, you're going to start seeing that some of what we're going to be doing is just determining yes or no, does that limit exist? Yes or no, does the function converge? Not necessarily what does it converge to. Sometimes we'll be able to answer that question, but not always. A lot of times it's more about just yes or no, does it converge? Okay? So I'm going to skip these two examples for now, and we will talk about those in class. I do want to get down to a couple more terms, though, just as introductory, so that we have plenty of time to get through the examples in the notes in class, okay? So right here we have that the sequence is bounded above by m, so m is some value, if a sub n is less than or equal to m for every n, and it is bounded below by some value m and m is just that boundary, if a sub n is greater than or equal to m for every value of n. Okay, so what does that actually mean? Well, that means that if there's some constant m, so I don't know, maybe we're looking at a graph and then maybe this is what our points do, our discrete points, and then we have some constant m, okay, and we know that all of the values in the sequence for every infinite term in the sequence, okay, if all of those values are less than or equal to this, then that means it is bounded above by m. And then likewise, if we had, terms that were up above here, then this one would be bounded below by m. So that just means you have something that is greater than or equal to all of the values in your sequence, or less than or equal to all the values in the sequence, okay? A real quick example that we're familiar with, if we went back to this cosine one where it just jumps between positive and -1, we could say it is bounded below by -1 and it is bounded above by +1, because that sequence will never go outside of that range of -1 to +1, okay? All right, and then if there is a boundary above and below, like the example of cosine or cosine of pi n, then we just say bounded, okay? So we can say bounded above, bounded below, but if both of those apply, then we just call it bounded, okay? And then a couple of terms that we're going to explore a little bit. LUB is just short for least upper bound, and then GLB is greatest lower bound, okay? So for example, looking at this one right here, let's look at the first one I drew, not the second one. Okay, so I know that m is greater than or equal to all of these values. Well, technically, if I put anything, so let's call this, I don't know, p. Right here, this is also a value, a height that would bound this function above, because these points never cross the height of whatever y equals p is. However, it's not the least upper bound, because there are values below that would also work as upper bounds. So m here, so this is an upper bound, but m in this case, because it appears that we approach a horizontal asymptote of m, m is the least upper bound, because it's the lowest that we can get without being below some of the points, or at least one of the points on our curve, okay? Last term here, monotonic. This is something that we saw in section 3.1 in the book when we talked about increasing and decreasing. Remember, we said that a function is strictly increasing or strictly decreasing on an interval if it is monotonic. So using the this notation here, it means a sub n is less than or equal to a sub n plus 1. So in other words, any term is less than or equal to its next term, okay? If any term has a value that is less than or equal to the next term, then that means the function is strictly increasing. And then if any term is greater than or equal to the next term, then the sequence is strictly decreasing. Okay, and then we have this theorem here that says every bounded monotonic sequence converges. So if it is bounded both above and below, then it has to converge to something. Okay, all right, and then we're going to do the examples from up above, and then these two in class.